Hello everyone and welcome to the Vibration Lab. This is your teaching assistant Nabil Abdul Razak. For this lab we have two videos. The first video is a brief introduction with the theory behind the Vibration Lab and some calculations. And the second video is the vibration experiment. The objective of this lab is to determine the first 5 natural frequencies and their corresponding node positions of a beam modeled as both free and cantilever beam. And the second objective is to calculate the damping ratio of a cantilever beam. So basically the vibration experiment is divided into 3 parts. The first part is to find and measure the location of the node of a free beam. The second part is to find and measure the location of the node of a cantilever beam. And the third part is to calculate the damping ratio of a cantilever based on an experimental data. Some theory behind the vibration lab. For the free beam, to the right we have the schematic diagram of a typical free beam. And here we have the information of the physical dimensions and also other properties of the beam that we use in this experiment. And some of the calculations that we need to do for this lab. For the frequency, we'll use this equation. And for the infinite root, which is P sub n times L, we use this equation for the free beam. And for the node position, we'll use this long equation. Now, if you use this equation to find the value of Bn sub L, you will end up with these values for the infinite root. If you use the root number from 1 to 5, and the free beam natural frequency can be calculated based on the values of the infinite root using this equation. E is the Young modulus, I can be found from this equation, rho is the density, and A is the area which can be found from this equation. So these are the frequencies that we will use in the experiment, and based on these frequencies we will find the nodes, and also we will locate the nodes on the beam and we'll collect the distance and the position of each node. Similarly for the cantilever, so now the cantilever is fixed from one end and free from the other end, as we can see in this diagram. And the frequency equation is the same. The only difference here is the length. For this experiment, the length of the cantilever is half of the length of the free beam. So we know that the length is 1 meter for the free beam. So this one is 50 centimeter or half meter. And also the equations will be the same. For the infinite root, the equation is similar to the equation that we saw in the free beam, except here the sign is minus instead of plus. So it's n minus half times pi. And the node position also is different. Now we take half of the node position. And here also based on the root number, we can find the infinite root number, which is based on this equation. And we have this 5 root numbers. And based on these 5 infinite root numbers, the frequency can be calculated using this equation. And we will get these values of the frequency for the cantilever beam. Now for the node position for the free beam, we will use this equation to calculate the theoretical node position. And to do that, you will need to use Excel. And in Excel, I put the equation, this equation over here. and I use the value of the infinite root and also the length and also the ratio of x over L. X is the step which, as instructed in the project description, you should use 1 centime at the time. So you have from 1 all the way to 100. And if you have your calculations right, you should get a graph like that. And the point at which the x sub n is equal to 0, it is considered as the position of the node. So right here, I have this 22 centimeter and 78 centimeters. So for this infinite root, we will have 2 nodes, and these 2 nodes position are 22 and 78. Now, if you change the infinite root and put the second infinite root, which is 7.8, and use the same equation, you will get 3 nodes, 13, 50, and 87. And now if you put the third infinite root, you will get 4 points, and so on until you reach the fifth infinite root, where you will get 6 points. So that's the way how you find the node position using this equation for the free beam. Similarly, for the cantilever, we will use this equation this time, where we have the whole equation is multiplied by half, and also the infinite root here is different for the cantilever, and also the length here is different, where we have 50. In the free beam, we have the whole length, which is 100 centimeter. And also for X, we will only use 50 centimeter steps. And based on that, the value of the X sub n for the first infinite root will look like this, where no node is indicated. Now, if we put the second infinite root, which is 4.7, we should get 1 node, and in this case is 40, at which the x sub n will equal to 0. And if you move on and put the third one, you should get 2 points, and the fourth one, you should get 3 points, and so on. And that's how we find the node position using this equation for the cantilever beam. So you need Excel to do the calculations and to find the node position for both the free beam and the cantilever. The cantilever beam damping ratio is equal to sigma divided by 2 pi, where sigma is the logarithmic decrement, and the logarithmic decrement can be found from this equation. To explain this equation furthermore, you will get a data set, and in the data set you will see this graph, and this graph represents the data of a damping beam that we collected in the experiment during the experiment. And now if you get a portion of this data, and based on this portion of this data, the x sub o, which is this one in this equation, is the initial x displacement, or is the initial amplitude, and the x sub n right here in this equation is the final or the last x amplitude based on the portion that you select from the original data. N is the number of the cycles. Now, if you count the cycles like 1, 2, 3, 4, and so on, you will find that the number of cycles is 39, and this is the N right here. And once you find sigma, now you can find the damping ratio. The next section of this video will be the vibration experiment, and it will be in a separate video.